Euler's identity is often voted as the most beautiful equation by mathematicians. Nobel laureate physicist Richard Feynman famously called it the most remarkable formula in mathematics. Euler's identity is loved because it blends 5 constants from seemingly distant areas of math: pi from geometry, e from calculus, I from algebra, and 0 and 1 from the numbers. Nevertheless, most material covering this identity involve advanced and unintuitive techniques like the Taylor series, which deviate from the formula's intuition and core. My goal is to present Euler's identity in an original light by linking its foundational mathematical ideas with intuition and real-world analogies, so you can appreciate the beauty of this identity too. The first thing we have to note about Euler's identity is that it is a special case of Euler's formula, e to the ix equals cosine x plus I sin x, where x equals pi. A special case just refers to a certain interesting instance of a general rule, like a formula. For instance, the 3-4-5 right-angled triangle is a special case of the Pythagorean theorem. To properly understand Euler's identity, we must first explore Euler's formula. Now, this formula may seem daunting, but I promise that this formula is very easy once you realize its key concept of circular motion. Let me explain. Real numbers can be modeled on a real line. Their position along the axis would indicate their value. Similarly, complex numbers can be modeled by adding another axis to the real line. We use this plane to represent 2 values with a single point, which is essential for a complex number since it has a real and imaginary part. The x value represents the real part of the complex number, while the y value represents the imaginary part. The reason we need the complex plane is to introduce the complex unit circle, a circle with a radius of 1 centered at the origin. An interesting property about this unit circle is that I can represent any of the points on this circle with a single number. How? Well, even though complex numbers themselves require 2 different values to represent, because every point on the circle is equally far away, we can represent each of them with an angle. For instance, this point, 1/2, root 3 over 2, can be represented with the value pi over 3 radians, because that's the angle it has from the positive x-axis. Now, take any point on the circle. Notice that we can draw a right-angled triangle to it, with the hypotenuse being the radius with length 1. The x and y values of the point would each correspond to the horizontal and vertical lengths of the triangle. Because the hypotenuse is 1, we can actually represent these sides with cosine and sine in terms of this angle. We can also notice that this is true for any angle on the circle. Using this, we can actually define a function that takes an angle as an input and gives out the corresponding complex number on the unit circle as an output. Zx equals cosine x plus I sin x. Does this seem familiar? This function, which traces the circle counterclockwise, is the right-hand side of Euler's formula. Now this is the essence of Euler's formula. Fundamentally, all Euler's formula is trying to say is that e to the power of I theta simply traces a circle in a counterclockwise motion. All that remains to show is that e to the ix traces a circle, and hopefully, in the process, explain how some of these specific constants can simultaneously appear in the way they do. Explaining Euler's formula can be done in many ways. Again, one of the most common ways is to use the Taylor series of the respective functions. However, this method is generally quite advanced and it fails to capture the beauty behind why these specific constants are needed. A more intuitive explanation can be found using differential equations. What are differential equations? A differential equation is an equation that connects an unknown function to its own derivative. A great example is the formula f equals f prime. In other words, the function f is equal to its derivative at any point. Here we can see that e to the power of x satisfies this equation, because its derivative is itself. Now consider differentiating the function zx equals e to the ix. We get z prime equals I times e to the ix by the chain rule. Interestingly, we notice that z prime equals I times zx. This is the differential equation that is essential for understanding Euler's formula. But what does this mean? An intuitive representation of this identity can be found by visualizing a field of road signs. In this field, at any given point, there is a road sign telling you which direction to go. At any point in the map, the direction the road sign is pointing you towards, or the derivative at that point, is determined by where you are on the map, multiplied by I. Though we commonly think of derivatives as instantaneous slopes, in this plane we can imagine that it is the instantaneous direction of travel along with the rate of change. What's interesting is that multiplying a complex number by I causes it to rotate by 90 degrees counterclockwise. This is because a complex number a plus bi multiplied by I returns negative b plus ai. This is true for all complex numbers, and we can see that negative b plus ai is indeed a 90 degrees counterclockwise rotation. With this knowledge, we can plot the full graph of this function given its starting point, because we can just follow the paths drawn out by the road signs. To do this, first we want to note that z0 equals e to the power of 0 equals 1. This gives us a starting point at the real number 1, or 1, 0. To find the derivative of this point, we rotate our radius to this point 90 degrees counterclockwise and move the starting point of this derivative to our point. Now imagine, what would it look like for a point to constantly move in a direction leftward and perpendicular to its radius? To visualize this, we're going to use some Lego. Let's put a car in the complex plane with its front tip at the point 1, 0. Normally, if the car points straight ahead, it travels in that direction. But now imagine that, wherever the car is, its direction of travel is always perpendicular to the line connecting its tip to the origin, pointing counterclockwise. What would happen if we drove it? The car traces a circle. This is because at every moment its direction is perfectly sideways from the origin, meaning it never moves closer to or further away from the origin. It simply moves around it. This is exactly what happens with e to the ix. Its direction of change is always the radius rotated 90 degrees counterclockwise, which is why it must trace a circle. We now know which direction e to the ix moves in, around the unit circle, but we still don't know how far it travels for a given change in x. To find that, we look at the magnitude of the derivative. The magnitude of the derivative tells us how far the point travels for a given change in x. Now, recall that z prime equals iz. Since z lies on the unit circle, its magnitude is equal to the radius, or 1. Multiplying by I only rotates a complex number, so the magnitude of z prime is also always 1. In other words, when x increases by 1, the point travels 1 unit along the circle. Now, let's take the formula for radians. Since the radius is 1, we can see that on the unit circle, the angle is equal to the arc length. Hence, traveling 1 unit means rotating by 1 radian, and an input of x rotates the point by exactly x radians counterclockwise. But the point on the unit circle at angle x is also exactly the point represented by cosine x plus I sin x. Therefore, e to the ix and cosine x plus I sin x must be an equal function, both tracing this circle. Everything we discussed has been culminating to this. E to the ix and cosine plus I sin x are equivalent circle tracers. For Euler's identity, we set x equals pi, or equivalently, we rotate our point by pi. The point travels halfway around the unit circle and arrives at -1, meaning e to the I pi is equal to -1. We can rewrite this equation to achieve the beautiful e to the I pi plus 1 equals 0. A question you might have at this point is why? Why convert trigonometric functions to an exponential one? Why convert complex numbers to an exponential one? The reason we use an exponential instead of trigonometric functions is because they're significantly easier to differentiate, multiply, and manipulate the frequency of compared to trigonometric functions. Perhaps one of the most notable uses of Euler's formula is Fourier transformations. Essentially, it's the process of displaying complex waves and signals as the sum of sine and cosine functions. Using Fourier transformation, we can break down complex waves into simple symmetric ones, as we can see in this example, just like how a prism breaks down light into its components. During this process, using Euler's formula to convert trigonometric functions into exponential ones make computation significantly easier. To wrap up, Euler's identity isn't just a cool formula, it's a crucial tool in modern technology. But I also think this reveals something important about maths in general. Euler could never have imagined the uses for his formula when he was alive. Math, to many, may seem like it dwells upon the theoretical and impractical, but I think at its core, math concepts are never truly useless. They're just waiting for us to catch up.